Good day, students. Today we are going to be about the Chinese remedial theorem, which is written in the short form CRT. So sometimes if you don't see Chinese remedial theorem and then you see CRT, which being the acronym, it's talking about the same thing, the Chinese remedial theorem. The Chinese remedial theorem is very easy, but it is a little complicated, so we must note and then focus as we go along. One thing that we must know about this is that we are talking about a theorem over here, and we learned previously what theorem means. We said that a theorem is a statement which has been proven. So we must know that the Chinese remedial theorem as well has been proven, but today our discussion is not on the proof of this theorem, but what we are looking for over here is how to use the theorem to solve congruencies. That's what we are coming to do today, how to use the Chinese remedial theorem to solve congruencies. In despite of that, let's state what the Chinese remedial theorem says. In stating the theorem, we let D be a principal ideal domain and a positive integer such that n is greater than or equal to 2, and we have a1 up to an all belonging to the principal domain D. If for every pair I and j belonging to a set of natural numbers up to n such that ai and aj are relatively prime, then for any a elements m1 up to n belonging to D, the principal ideal domain, for any there exists a certain number x will belong to the principal ideal domain D, which satisfy all the congruencies that we have below. And the congruencies we have x being equivalent to m modulo a1. Also we have x equivalent to m2 modulo a2, and x equivalent to m3 modulo a3 up to x equivalent to mn modulo an. We can go on and on and on. The mn modulo an specify the number of congruencies that you are dealing with. So when we come back to what the theorem says, let's try to explain what the theorem says. If you have a domain D, which is the principal ideal domain, what the theorem is saying is that you cannot deal with equations less than 2. So that's why we have n, a positive integer, such that n is greater or equal to 2. So the n specify the number of congruencies that we are going to deal with. And under the Chinese remainder theorem, it specified that the number of congruencies should not be less than 2. So it should be 2 and above, and that's what we have here. And when you come, you can see that we have a place which says said that a1, ai, and aj are relatively prime. So under the Chinese remainder theorem, when we take the congruencies that we have over here, we can see we have x to be equal to some certain values, m1 in modulo a1, m2 in modulo a2, m3 in modulo up to mn in modulo an. What the Chinese remainder theorem is saying is that we have a certain value x which belongs to the principal domain, such that it will satisfy all these congruencies over here only and only if all these values or elements over here m1 up to mn are relatively prime. So one thing that we must note over here is that the Chinese remainder theorem fail to apply over here if these values over here, m1, m2, m3 up to mn, are not relatively prime. So if these values over here are not relatively prime, then this theorem, which is called the Chinese remainder theorem, will fail to apply over here. Okay, so let's take this example over here. We are asked to use the Chinese remainder theorem to solve the congruency that we have below. X congruent to 6 mod 7, x congruent to 4 mod 8. So when we are asked to use the CRT to solve congruencies like this, what the Chinese theorem try to establish is that we are looking for a value of x which in modulo 7 will give you 6, and also in modulo 8 will give you 4. So that's all we are looking for. So first, we got to transfer all these congruencies into equations. In other words, simultaneous equations. So first, by writing all these ones in simultaneous equations, it will give us something like this. So this implies that in simultaneous equation, the first one will be having x to be equal to 6 plus 7a. So note and see how I've written the first equation. So let's name that one equation 1. So we have x now equal to, non-congruent to, x equal to 6. Then now the modulo has turned to plus 7a. Then now the second one, we have x congruent to 4 mod 8. So we can represent the mod 8 by another variable. So we can write this one to as x being equal to 4 plus 8b. And this one will be our equation 2. Beautiful. So now we have to solve this one simultaneously to get the value of a and b. But you can see that we have 3 variables over in actual sense: x, a, and then b. So this is how we are going to go about this one. What we are trying to establish over here is to find a value of x that will satisfy this equation that we have over here. So now what you need to do over here in reference to the Chinese remainder theorem is to eliminate x first. So by trying to eliminate x, we can see that if equation 1 is being subtracted by equation 2, we will be able to eliminate x. So by doing that, we'll be having 0 to be equal to, now we have 6 minus 4, so we have 2 over there. Then now we have 7a minus 8b, so we are going to have plus 7a minus 8b, and that's what we have over there, 7a minus 8b. So now we can try to make any one of the variables a subject. So now because the negative 8a is negative, when we transfer it to the other side become positive, it will be easier for us to make that one the subject. So we can say that 8b will be equal to 2 plus 7a. So here, to get the value of b, we have to divide by 8. So by dividing by 8, plus I will be having b to be equal to 2 plus 7a all divided by 8. And that's what we have over here. At this juncture, we have to get a value of a that will make the value of b to be an integer. and if possible a positive one as such, but the lowest integer b can be. So listen again. We are looking for an integer, but a lowest positive integer that b can be. So you must choose a value of. So here you must try to choose a value of a that will cause the value of b to also be an integer. So the value of a note should be an integer that will cause the value of b to also be an integer. So in simple terms, the value of a that you must choose over here should cause the numerator to be divisible by 8 without a remainder. So that's what you must note. You can choose an integer, but the lowest integer. Here, because we don't like negatives, I'll try to go with the positive integers. So I'll try to choose a positive integer of a that will make b also to be a positive integer. So let's take it like you choose a to be equal to 1. You can see that when you choose a to be equal to 1, the top will be 2 plus 7, because a is equal to 1. 2 plus 7, which will give you 9, divided by 8, you will not get a positive integer of b. So what if we choose a equal to 2? So we can see that when we choose over here a to be equal to 2, what will happen to b? We'll be having b to be equal to 2 plus 7 times 2. All this one divided by 8. And this clearly shows that b is going to give us, so you can see that this place will be 14 plus this 16 divided by 8. This one will give us 2. So this implies that when a equal to 2, b is also equal to 2. So we have our values over here. So with the values of a and b that you found, you go back to the equations that you created from the beginning of the solving. So we go back to the equations that we created and put any of the values of the variables into any of the equations and get a value of x that you want. So now when we go back to the equation 1, we have x to be equal to 6 plus 7a. And from what we did, we got a to be equal to 2. So by put a equal to 2 into equation 1, this implies that we'll be having x to be equal to 6 plus 7 times 2. We have our equation 1 over here, and in place of a, which is 2, we place it over there. So we can see that clearly our x will be equal to, so you have 14, so our x will be equal to 20. The same way, if you put the value of b into the equation 2, you also be having x to be equal to 2, and to be equal to 20, and that's what we have over there. So this means that the x that we are looking for that will satisfy the congruencies that we have is equal to 20. So in other way, to write the general solution of this, which is written as this, gs of equation 1 and 2, this is how we write the general solution. Is equal to the x1 plus multiplication of the modulus. So the modulus, we're dealing with mod 7. So let's, the first modulo m1 and the second modulo m2. times a variable g. So here our x1 that we found over here, so this one is the x1. The x1 is the solution from the equations that we created. So our x1 over here is 20, then plus, okay, so by writing the general solution, we have the x1 being 20 plus the m1 being the first modulo. So the first over here in the congruences we have here modulo 7. That's what we have at the top. So we are dealing with mod 7. So that's why we have the m1 to be 7 over there. Then the m2 is the second modulo, which is 8. And that's what we also have over there. So we have the general solution to be equal to the first solution, or the first s that we found from our equation that we created, plus the multiplication of the various modulos in the congruences times a variable, where this variable g belongs to the set of positive integers. So the variable g over here belongs to the set of positive integers. So in writing this one, we have the general solution to be equal to 20 plus 56 g, where g belongs to a set of positive integers, and that's what we have over here. So you can see the overview of the solution over here. After completing everything, we must try to test. So if really g belongs to a set of positive integers, 0 is also a positive integer. So this means that if g is equal to 0, what will happen? So now we are coming to test the solution in the work that we did. So if g is 0, this is what will happen. If g is 0, this means that, so we have the general solution over here. So if g is equal to 0, then this means that we'll be having the general solution. So over here, let me draw a little line. So if g is equal to 0, this implies that the general solution of equation 1 and 2 will be equal to 20 plus 56 times 0. So you'll be having something like this, 20 plus 56 times 0. And this one will clearly give us 20. So we are coming to test whether 20 will satisfy the congruency. So when you come here, we have x to be equal to 20, or the general solution to be equal to 20. So this means that when you put it inside, x equal to 6 in modulo 7. And now we said the x equal to 20. So we have to find the value of 20 in mode 7. And we can see that 20 in mode 7 is clearly equal to 6. The same way, it must also satisfy the second congruency, which is s is congruent to 4 mode 8. When you put 20 there, you can see that 20 in mode 8 is clearly equal to 4. So this means that 20 is one value or one particular solution to the congruencies that we have over here. The same way, when we take the general solution, if g is equal to 1, let's see what will happen. If g is equal to 1, from the general solution, you can see that our general solution of equation 1 and 2 will now be equal to 20 plus 56, since the g is only 1. And this one will clearly give us 76. When we put 76 in the congruency over here, we can see that 76 modulo 7 will be equal to 6. And let's see whether it will also satisfy the second congruency. When you put x to be equal to 76, we can see clearly that 76 modulo 8 will also give us 4. So we can see that the general solution that we have over here is correct. So this is how we use the Chinese theorem to. Okay, so we have a full question over here. State the Chinese remainder theorem. That's question A. B. Use this theorem to find the general solution of the simultaneous congruencies. So the statement of the Chinese remainder theorem, we learned and explained it just now. So for that place, I hope that viewers are conversant with it. So now let's proceed and then find the solution or the general solution to these simultaneous congruencies that we have over here. We have 3 of them. The first example that we did was on 2. So see how when they are more than 2, let's see how it works. So first we have to transfer all these congruencies to equations. So by transferring them to equations, we have our solution. The first one, we have 2x congruent to 2 modulo 3. So we can write this one in this form. 2x to be equal to 2 plus 3a. This equation 1. In 2, we can write it in this form. 3x equal to 1 plus 4b, equation 2. Then the last one, x is equal to 2 plus 5c. So we have it over here. So beautiful. Here, if you have the equations to be more than 2, you take them in pairs. So first, we have to take only 2 of the equations. Then find the general solution for that, for those 2 equations. And then now come and link that general solution together with the third equation and find all the general solution for the 3 equations. So saying it in words, some will get confused. So let's get to work. So by solving, so we take equation 1, which is plus 3a, and then equation 2 only. So we have 3x is equal to 1 plus 4b, which is equation 2. Now our main aim over here is to eliminate the value of x. So if you want to eliminate the value of x when you are solving simultaneous equation, we can multiply this place, which is through equation 1 by 3, and then through equation 2 by 2. So that's what we have over here. So the first one, this implies that we'll be getting something like 6x to be equal to 6 plus 9a. So that's what we have for the first one. The second one will also give us 6x is equal to 2 plus, this one will give us 8b. So that's what we have over here. So by subtracting the both of them, that means the down from the top, we'll be having 0 over here is equal to, this one will be giving us 4, then this one will give us plus 9a minus 8b. So that's what we have over here. Over here, I said we have to make one of the variables a subject. So you can see that because the 8b is negative, let's push it to this place so that it becomes positive. So this will imply that we'll be having 8b to be equal to 4 plus 9a. When we divide through by 8, This will give us b to be equal to 4 plus 9a, or this one divided by 8. So we can see what we have over here. So over here we must choose a value of a. So we can choose any integer, but because of the negatives. Okay, so by choosing a value of a, which is an integer, for here I'm choosing a positive integer, which will give you a lowest value or lowest integer of b. If we test a to be equal to 0, we can see that we'll be having the numerator over here to be 4, and the 8 will not go into 4 without remainder. When you choose 1, we'll be having the top to be 13, 8 cannot go into 8. 2, when we choose 2, a to be 2, the same thing will happen. When we choose a to be 3, the same thing will happen. Unless we get to a, when we choose a to be equal to 4, see what will happen. We'll be having b to be equal to 4 plus 9 times 4, or this one divided by 8. So we can see that clearly the top is going to give us 40. So we have 4, and then this one will give us 36. So 36 plus this will give us 40. And 40 divided by 8 will give us 5. So this means that when a is equal to 4, b will be equal to 5. And that's what we have over here. So quickly, we must make sure to input these values into any of the two equations. So we can say we can put a into equation 1 or b into equation 2. When we do that, we'll get the same value for x. We'll get the same value for x. Okay, so by putting a into equation 1 or b into equation 2, you get the same answer. So first, let's do that for equation 1. So putting a into equation 1, so put a into equation 1, we'll be having 2x to be equal to 2 plus 3 times 4. So that's what we have over here. And we'll be having 2x to be equal to, so we have 2, this one is 12, we have 14. And clearly, x is going to give us 7. The same way when you test for, so let's test for the second equation. By putting b into equation 2, we'll be having 3x to be equal to 1 plus 4 times 5, because b is 5. And here you'll be having 3x to be equal to 21. And clearly, x will also give you 7. So you can see that no matter, because you use the two equations, no matter which of the values you insert in the appropriate equation, you get the same value for x. Don't forget, this one is the initial solution that we got from our equation. So this one is the x1. So to write the general solution of equation 1 and 2, this is because we dealt with equation 1 and 2 only. So this means that the general solution for equation 1 and then 2 should be equal to, we said, the x1 plus m1 times the m2 times a variable. So let's take this one, gene. Okay, so this is equal to, our x1 is 7 plus the m1 is the modulo from the first equation, and that's mod 3, times the m2 is the modulo from the second equation, which is 4, times g. So we have our general solution of equation 1 and then 2 to be equal to 7 plus 12 G. So we have this general solution over here, where G belongs to a set of integers, positive ones. So this is what we should note. So this is the general solution for the first and then the second equation. So to find, so this is the general solution for the equation 1 and then the equation 2. So to find the general solution for the three equations, we got to write this solution for equation 1 and equation 2 in an equation form. This is the general solution. So this means that the x is equal to 7 plus 12 G. Don't forget the x1 is a particular solution. So you can see that at G equal to 0, you get the particular solution of 7. So this means that the general solutions goes on as the value of G changes. So you can get different particular solutions. So when G is equal to 1, the solution that you satisfy the congruency of 1 and then 2. When G is equal to 2, the solution that you get to also satisfy the solution of the two congruencies that we transform into equations and solve. So particular solutions will be obtained as the value of G changes. So this one over here is a general solution. That's why we have x. So x changes as G also changes. That's why we have the general solution to be written in this form: s equal to 7 plus 12G. So we can name this one equation 4. So we have equation 4 over here. And let's not forget, we have not finished solving for the whole of the three equations that we started with. So the last equation, equation 3, is equal to 2 plus 5c. And this one is equation 3 that we have over here. So we can see that over here, to solve this one simultaneously, it will be so easier because we don't have any coefficient of the variables x. So we can simply say that we can subtract equation 3 from equation 4, or we can choose to subtract this from this. No matter the way we do it, it will still work. So we can say that from here, we can subtract equation 4 from equation 3. So we can say equation 3 minus equation 4. So in that form, we'll be having this place to be 0 and this place to be equal to, since we are subtracting 4 from 3, this one will be getting negative 5. Then from here, we'll be having 5c minus 12g. So that's what we have here clearly. So we have it over here. So from here, we must make one of them the subject. So we can see that because the g is negative, we must send it to the other side. So we can write this in this form: 12g to be equal to negative 5 plus 5c. So that's what we have over here. So to make g the subject, we'll be getting g to be equal to 5c minus 5, or this one divided by 12. So here too, we must also find values of g, values of c, which are integers or positive integers that will make g to also be an integer, a positive one as such. So we can see that we must test values from 0 up to wherever we get a numerator which is divisible by 12 without a remainder. Okay, so we can see that after testing all positive integer values of C that will satisfy this whole fraction becoming a whole number or a positive integer. Only a value of C being 13 will satisfy this whole issue. So if C is 13, let's see what will happen. If C is 13, we can see that G will be equal to 5 times 13 minus 5, all this one divided by 13, all this divided by 12. That's what we have over here. So we can see that when we simplify this whole fraction that we have, we can see that G is going to give us 5. So this clearly shows that at C equal to 13, G will be equal to 5. And that's what we have over here. So from here, we must put these answers into any of the equations that we have. So the third equation, let's remind ourselves what the third equation looks like. The third equation is x equal to 2 plus 5c. That's the third equation. And then the fourth equation was the solution to the two equations that we started with. And that one gave us x is equal to 7 plus 12g. That was the fourth equation over here. Anyhow you put it, you get the value of x to be the same. So let's take the third equation and put 13 over there because we have c in the equation 3. So we can say put c equal to 13 into equation 3. And by doing that, we'll be having x to be equal to 2 plus 5 times 13. And this clearly shows that x is going to give us, so we have this plus this plus this, so x is going to give us 67 because this time this will give us 65. So that's what we have here clearly. So don't forget, we solved the first two equations and we got a general solution for it, and that general solution was transferred to an equation, and we compared that equation with the third equation and solved and got a particular solution. So this solution over here, x equal to 67, is a particular solution for all the three equations. So this one is an x1 for all the three equations. So x1 is equal to 67. To write the general solution for all the three solutions, we have the general solution for the three equations. So for equation 1, equation 2, and equation 3, this one will be equal to the x1 plus, so we said now we are going to deal with the product of all the modulos that we are dealing with. Don't forget, we are dealing with three congruencies, so three modulos will appear here. So we have m1 times m2 times m3 times, maybe let's take a certain variable d. So don't forget, if you are dealing with four congruencies, you will have this side to be a product of four modulos. So here we have this one to be equal to, our x1 is 67 plus the first congruency that we were dealing with, or the first modulo that we were dealing with was 3, then times the second one was 4, times the last one was 5. And that's what we have over here. So clearly, So by writing the general solution for the three congruencies, we have general solution for question 1, question 2, question 3 to be equal to 67. So we have 3 times this will give us 12. 12 times 5, this one is going to give us 60. So we have plus 60D. So this is the general solution for the congruencies that they say we should find the solution to. Don't forget where D belongs to a set of positive integers. So that's how we have over here. So let's do some testing. We want to do some testing. Let's take the general solution. We have the general solution of question 1, question 2, question 3 to be equal to 67 plus 60D, where D belongs to a set of positive integers. Let's say like D is 0. If D is 0, let's see what will happen. If D is 0, then that means we'll get a particular solution X if D is 0. So if D is equal to 0, we'll have a particular solution X to be equal to 67 plus 0, and this one is equal to 67. So let's take 67, whether 67 satisfy these congruencies that we have over here. When we take the first one, we have 2x congruent to 2 in modulo 3. So let's test for that one. We have 2 times 67. That's for the first one. This one, because we have 2x over there, so this one is going to give us 134. 134 in modulo 3. 134 in modulo 3. This one is clearly going to give us an answer of 2. So that's what we have over there. So 134 in modulo 3 is going to give us 2. And that's what we have over there. And that's what we have at the top there. The congruency says 2 times the x is equal to 2 in modulo 3. So let's take the second one too. The second one is 3x. So let's take 3 times 67. This one is really going to give us 201. 201 in mode 4 is clearly equal to 1. And that's what we have over there. So you must note. And the last one is x. So the x which we found was 67. So 67, so we have 67 in mode 5. And clearly this one is equal to 2. So we can see that the value that we have over here for the x when D is equal to 0 satisfy the whole congruencies. So what we must note over here is that as the value of the D changes, the value of the x will change, and that means that the particular solution will change. So you don't have just one particular solution. We have one particular solution of 67 when only D is 0. If D is 1, you have another particular solution which will also satisfy the congruencies that we have. So you can test on your own at home and see what I'm talking about. We should know that when you solve a congruency or you solve a set of congruencies and you get any solution for it, it is called an inconsistent system or inconsistent system of congruencies. So this is all that you need to know about the Chinese remainder theorem. Okay, so the general solution that we have can also be written in another form. You can see that When we transform this congruency, so let's take for example this congruency that we have over here, 2 mod 3. When we're transforming this one into an equation, we wrote it as 2x is equal to 2 plus 3a, and that's what we did. So the same way, if you have the general solution, you have of equation 1, equation 2, equation 3, which we got to be 67 plus 60d. This one can also be written as, so this one is the same as 67 mod 60. So if you don't write it in this form, you can also write it in this form, and that's another way of writing this general solution. So one thing that you must know is that we started with 2 congruencies, and now we have dealt with 3 congruencies. The same way, you can also be given 4 congruencies. First, you note, you transfer all of them to equations, then you start solving them simultaneously. So you start by pairing them. So you take the first 2. After getting a general solution for the first 2, then you transfer the general solution into an equation. Then you solve it with the preceding one. After getting a general solution for that one too, if they are more than 3, you continue. The reason why we stopped at this place is because we are dealing with 3 equations only. That was why when we got the general solution for 3 of the equations, we stopped. If you were to deal with 4 equations and you stopped, that means you have not gotten a solution for the whole system, but you got a solution for just 3 of the congruencies. So if there are 4 congruencies, that means you must generate 4 equations and then get a general solution for the 4 congruencies that we have. This and many more we should expect in our next video on this same theorem that we have over here. So have a nice day till we meet again. Bye bye.